Okay. Hello, mga ka-Gigi. Welcome back. So here I am, as per request from our dear students. We will tackle about Pascal identity. Pascal's identity was probably first derived by Blaise Pascal, a 17th century French mathematician whom the theorem is named after. So the problem that we're gonna tackle now is about Pascal's identity. So we're gonna prove Pascal's identity. Then let me share the screen with you. Ta-da! Pascal's identity. A bit loading. Let's wait a bit. There, Pascal's identity. First problem we have here, and that would be the last problem we have here also. Prove Pascal's identity. So that's the Pascal's identity. So we're going to prove it. But before that, always remember the binomial coefficients. In mathematics, the binomial coefficients are the positive integers. Let me read. The positive integers that occur as coefficients in the binomial theorem. So we have here a binomial coefficients n and k. Commonly, a binomial coefficient is indexed by a pair of integers. A pair of integers satisfying n is greater than or equal to k, greater than or equal to 0. N and k, it is also written as, binomial coefficient is written as n and k, like this. The binomial coefficient n and k is the number of k elements subset of the set n. So, subset of the set n. That is, n and k gives the number of different ways to make k choices given n total of options. Okay. My nose is a bit itchy. If the order in which the choices are made does not matter. So here is the thing to remember. If the order in which the choices are made does not matter. To compute for our n and k, or the binomial coefficient n and k, we have the formula. Always remember this formula. N factorial all over k factorial multiplied to n minus k factorial. So, to prove our identity, we need this formula. Oh, welcome back. Where are we again? So here we are. Let's move on to the next slides. We're done with this part. So the problem we have, the first problem, and the loss as well. to prove Pascal's identity. I keep saying this, but let's move on. But before that, in order to prove Pascal's identity, we need to learn the theorem itself. Pascal's identity states that the n and the binomial coefficient n and k is equal to the sum of n minus 1, k minus 1, and n minus 1 and k, such that for any positive integers k and n. So here, our binomial coefficient n and k can be expressed in these common forms we have here. These forms. So it involves the C here, the combination. Um, for those who doesn't know yet, combination is a mathematical techniques that determines the number of possible arrangements in a collection of items where the order of the selection does not matter. So as I said earlier, if it talks about the order in which the choices are made doesn't matter, we are talking about the combination. So we'll do it that way. Next, let's move to the next slides. Oh, not next slides. There's follow up. Okay, let's read the problem that we have. This result can be interpreted combinatorially as follows. The number of ways to choose k things from our n things is equal to the number of ways to choose k minus 1 things from the n minus 1 things added to the number of ways to choose k things from n minus 1 things. So we're just reading the problem that we have. And always take note to remember this. The binomial coefficient n and k is equal to n factorial all over k factorial n minus k factorial. So here's the proof that we have. So if k is greater than n, then our binomial coefficient n and k is equal to 0, equal to n minus 1, k minus 1 plus n minus 1 k. And so the result is trivial. So assume that k is less than or equal to n. Then if we assume that they are less than or equal to our n, then our n minus 1, k minus 1 plus n minus 1, k expressed in factorial form. So we express it like this one. So suppose this will be our n and this will be our k. So you just express it like this. N factorial all over k factorial minus k factorial. Then we do the simplification. Charot. Simplify. Let's simplify the problem that we have. Okay, what happened here is we do factorization. So we factor out n minus 1 factorial and simplify the left terms in that side here, in this side here, and get their common denominator k factorial n minus k factorial. Then move to the next portion. So we have now, by simplifying this one, it come up with n all over k factorial n minus k factorial. So we have this problem. Let's focus on this portion here. And we can express now that way. N factorial is all over k factorial n minus k factorial. And this one is equivalent to this portion here. And now that is equal to our binomial coefficient n and k. And that's all for this Pascal's identity. Thank you so much.